Okay, so good morning, everyone. So the first speaker this morning is Fedor Smirnov from Jussieu, telling us about diagonal finite volume matrix element in the SinhGordon.
Okay, so first of all, let me thank the organizers for opportunity to be here and to talk here. And so I have chosen to talk about this, about the field theory, integrable field theory. So probably I would better talk about the latest so here, but so probably so to just to have some change, I will. It's just more interesting to me. But so anyway, so we consider, let's consider an Euclidean quantum field theory on a cylinder. And so my problem is to compute the one-point functions. Yes, so I put a local operator somewhere here, and then I compute a partition function like that. And so I have energy momentum tensor, and so I have light cone here. I write light cone components of the energy and momentum computed on these states here. So these are supposed to be eigenstates of the energy and momentum. So and then my goal will be to compute these expectation values when these two eigenstates here are the same. And there are several reasons to be interested in these quantities. So first of them, oops, yes. So first of them is that when L, the length of the cylinder, goes to infinity, then of course whatever boundary, normally whatever boundary condition I start with, so it will, so when the cylinder is infinite, it will look for the ground state, yes, because the eigenvalue of kind of transfer matrix will be the maximal for the ground state, and it is, if it is infinite, so this is the only one which will survive. And then these one-point functions are in principle important for computation of any green function. If I use the OPE, OPE in principle is a purely ultraviolet characteristic of the theory. So it's computed for short distances at least. So in principle, it can be computed from perturbation of conformal field theory, yes, of corresponding conformal field theory, and then all the multi-point functions will be reduced to these one-point functions, which are the only quantities which depends on the environment, on the for example, on the radius of my cylinder, on the eigenstate, on the ground state, and so on. So this is one application, but this is for when I take the ground state. And so this kind of matrix elements were computed long ago. So another thing is that why these diagonal matrix elements in general are interesting, because, for example, so if we want to compute the one-point function on a torus, which is an important quantity, then and Ivan Kostov was talking about the partition function of the torus, but so if we want to consider one-point function of the torus, which are again applied to any correlation function, but already on the torus. So then this is the sum. This is the sum over all the eigenstates and of this diagonal matrix elements normalized. And so interesting thing is that we will see the formula later for this matrix elements. And so in this formula, the dependence on the radius of the cylinder, on the length of the cylinder are absolutely different. And it will be interesting to check, at least on the computer, that they coincide. If I interchange, because it's on the torus, I can interchange, yes, L and R. And also diagonal matrix elements are used for calculation of S matrices, of corrections to S matrices, if I at least for two S matrices 2 to 2, if I make a perturbation of my integrable model. So now I will be considering one particular model, which is SinhGordon model. So here is the Lagrangian density, and so I use some strange normalization here, but it is useful to me. And SinhGordon model so is known to be invariant under B to 1 over B. So there is such a duality, important duality here, and we'll often use the self-dual kind of self-dual parameter B plus 1 over B, which is, so everybody, okay, not everybody, but many people know that this is an important thing, in particular in closely related Liouville. So then the spectrum is very simple in the infinite volume. The spectrum is very simple. So it consists of one particle, and there is an exact formula due to Alesha Zamolodchikov for the mass of these particles in terms of my parameter mu here. So you see, so this field has non-trivial scaling dimension. So that's why, so this m squared here is not mass, but mass to some power. And so this is so there are some constants which are horrifying for the first view, but so they are very useful for numerics. And so the S matrix is the simplest one. So this is a scalar particle factorized scattering, and so the S matrix is as simple as that. And in what follows, I will use the dimensionless parameter, which is mass by radius of my cylinder. So then how the spectrum so I am talking now about, so here is my cylinder, yes. I am talking now about this periodical problem. So the spectrum is basically, to make the story short, is reduced to finding all the solutions. So there is the function which is regular in the entire, so it's an entire function in the place of in the plane of theta. Theta is rapidity, and it satisfies the following relation. And the asymptotics when theta goes to plus minus infinity along the real axis is like that. And so to find the spectrum of SinhGordon model in a finite volume, it is sufficient to enumerate all the solutions to these equations which are real, with real roots. And so, sorry, once again, so with real roots in the strip from minus pi to pi along imaginary, but then there will be additional roots, but this is not already, they are already characterized. So in this case, the Q is like that. So these are roots, and this is something else, so something which is which does not vanish in the strip. And then we introduce so this guy we denote by e to minus epsilon of theta, And for this E, we find the equation like that, which is TBA, yes. K here is a logarithmic derivative of S. And so additional equations are for rapidities of these particles here, or if, I don't know how, let's call them particles. So they are like this. So these are integers. So, and then, yes, F is something. So then you have this system of equations. And of course, so it does not look very simple, but so the point is that the iterations, so you iterate, and the iterations for the system of equations converge much faster than for any linear equation. So if you put it on the computer, you immediately find with huge accuracy whatever you want. So the spectrum. So, and yes, and it's convenient for me to use minus S here because S matrix is -1 at 0, so it's better to do it this way. And then if so this is an integrable model. So in addition to the energy and momentum, I have infinitely many local integrals with all odd spins. And so the eigenvalues are given by this formula. And so I introduce here some constants because I want to, I will soon talk about relation to the ultraviolet conformal field theory, and these constants are needed in order for normalization. There are some important constants which were introduced by Bazhanov, Lukyanov, and Zamolodchikov. They're here. So in particular, so the energy is sum of these two guys for S equal to 1, and momentum is difference. Yes. So now let's see. Now we come to some ingenious part of the story, which is due to Sasha and Alyosha Zamolodchikov. And so this is like that. So everything actually depends on this dimensionless parameter. And now suppose that radius is small. Then it's easy to see that the potential in I consider the field phi. And so there is a zero mode and then oscillations. So, and the zero mode is getting like that. So it goes further and further when R goes to 0. And so then a good approximation to the spectrum in this limit. So in this limit, so what does it mean? So this limit, so we have two walls like that. So these are two, if you wish, two Liouville's, which are not very two Liouville series, where I replace my cosine hyperbolic in the Lagrangian by exponent. And so, and there are two Liouville's which are rather far one from another. And then as a good approximation for the spectrum, I take just quantization of the zero mode. So this is a quantum mechanics a particle which travels in this potential and with reflection. And the reflection is known. So altogether the spectrum in this approximation, so this is the reflection matrix, if you wish. So the spectrum is defined by this equation, actually with very good precision. So, and then here I can compare, for example, I solved this equation and I had the normalization before, which gives me, which relates me to the conformal field theory, to the Liouville case. And so then I can compute, for example, the energy and momentum from this, so compute this, then the energy and momentum with the formula which I had before. On the other hand, I have this simple CFT formula. And so either use my TBA or use this equation and compare. And we see that we're doing very well for small radius. So here radius is 10 to minus 3. If I would take 10 to minus 5, they will be already, you will never distinguish them. So here's the table. So I want now to identify, I had this, so let's see, let's go here. So I have the, I have descendants of in the conformal field theory, I have some descendants of some Virasoro descendants, and so here are energy and momentum. Yes. So on the other hand, I compute my. Let me see. I compute the integrals of motion using these numbers here, yes, from TBA equations. And so I want to identify them. And so here's the identification. So n, I take n's like that. I take, so this is so there are two things. So from Virasoro side, I can have primary fields which are shifted, and I have descendants. And so here is the shift of the primary field, and here are the descendants. So I don't know. So this is the table. So the only thing which I want to say here is that you see, starting from here already, this 4 and 1, 3 already energy and momentum do not distinguish between these two states. So we will return to that. They will be distinguished by the next integral of motion, next local integral of motion. Okay, so now I am back to my problem. I want to consider these matrix elements, yes, for the states which are computed from, I don't know, from the TBA. The thetas are not arbitrary, they are solutions to these equations which I mentioned before. So in the conform, and the important thing is that I suppose to have one-to-one correspondence between the fields in ultraviolet limits, so in Liouville, if you wish, and in the massive model. This one-to-one because so I will consider arbitrary exponents here. So and then just for dimensional reasons. So if there are no contour terms which can be added for arbitrary dimension here. So anyway, so this is one-to-one correspondence. So that's why in SinhGordon model, I count the local fields in the same way as in conformal field theory. The conformal symmetry is lost, of course, but it is used as a for counting the fields. So I consider these matrix elements for this, the primary fields. I normalize them by Lukyanov and Zamolodchikov one-point function for some reason, which I will explain. So, and I don't write the expression for this one-point function. So if you know it, it's all right. If you don't, that's also okay. So, and the main, my main arm is the fermionic basis. Yes, so about which probably I was talking here some time ago. So I have some so I create, normally I create the descendants from primary field by Virasoro. But here I say that there is another way to create descendants which is related to the Virasoro descendants. The descendants are created by some fermions. There are two of them here and two of them for one chirality, two of them for another chirality, and the only requirement is the number of betas, this and this, beta and gamma. Betas is equal to number of gammas. So this is the requirement. So yes.
Because we are considering there is a conservation law describing momentum around the cylinder.
Yes.
The states which you consider, we assume non-zero momentum.
I prefer zero, yes. But yeah, okay, yes, I prefer. I think it's not so much. It's not so important. Yes.
Obviously, this momentum is an integral motion.
That's right.
But it's given in space.
Yes, right.
The question is, since there are two edges, two bases,
Yeah, yes.
could it be that there are two integral motion, one for the left base and another for the right
I am saying that yes, I am saying that here they're the same. I consider diagonal. In general, yes. In general, of course, yes. Mm-hmm. Yes. Because so if you don't have the insertion, then of course not. But if you inserted something, then yes. 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 Sure. Yes. And yes. And then actually there is a number m, which is the difference between number of betas and gammas for one chirality. And so it's interesting that my fermions, they create, starting from one primary field, they create more than Virasoro. They create not only Virasoro descendants, but also Virasoro descendants of all fields like that. So, and now how this happens. So I have a formula that first of all, these guys with negative indices are of course annihilation operators, and so these are commutation relations. So I introduce some T here, and so then if I want to create something on something with descendant of shifted field, so this is created by descendant of unshifted field with with something here, with some combination of these fermions here. So I will give some example. So now, and what is the reason? So actually, what I'm saying about here have not been computed. So this was rather conjectures, and that's why I need some checks for these conjectures. But what they are based on? They are based on SinhGordon, analogy with SinhGordon, where in SinhGordon these results were obtained as a scale. This fermion basis was obtained as a scaling limit from some inhomogeneous XXZ chain 6-vertex model, so which probably makes happy the audience. Yes. So now so first we constructed, then we make the scaling limit. So we will look at these fermions, and we realized one important thing that you see. So if we are talking about SinhGordon model and SinhGordon models the same, more or less. So then there are two symmetries. So first of all, of course, there is a symmetry. So if I take my primary fields into A phi, of course, so the one-point functions are symmetric under A2 minus A just because of C symmetry. Yes, so that's clear. But so on the other hand, I can consider it in some sense as a perturbation of Liouville, and that then it should inherit another symmetry, which is A to Q minus A. This is a typical symmetry for the Liouville. And so the property which actually defines this my fermionic basis is under both of these two reflections. So just my fermions beta switch to gamma and gamma. So this is a basis which respects this both symmetries, and this is what was called by I don't know, by Lukyanov to the Molodchikov, Fateev. So this was called by reflection relations. So in some sense, my fermions solve the reflection relations. So this is okay. So but this is a purely algebraic property. But so what is the important conjecture here is that the one-point function for the descendant created by these fermions are given just by determinants of this kind, yes, of one matrix, infinite matrix, or half infinite matrix, infinite. They are both, yes, so, yes, infinite matrix like that. So, with which I will describe in a moment. What time is now? Okay. So anyway, so the conclusion is that up to now, the conjecture is that there is such a basis in the. So we start with the conformal field theory, if you wish, yes, and we consider the massive field theory for which this conformal field theory this Liouville is an ultraviolet limit. So we count the fields by conformal field theory, right? So and then there is, in addition to the Virasoro basis, so there is another basis for which the one-point functions are easy to compute. Already for the interactive model, for the massive model, for the information. And so they are given by determinants of some matrix. So my next step is to describe this matrix. And this matrix, so actually it is basically, so this omega mn, there is a function of two variables, and these are just asymptotic series of this function into variables give me this matrix. And this I had to guess, but it must satisfy some additional properties and can be guessed. Then in principle, the program was also to guess it for the case of non-diagonal matrix element when we have different states to the left and to the right. But then the pandemic happens, and so we decided we had no time to work on that. So I mean, both of us. So this was with the work I forgot to say is with Zoltan Bynok, but so both of us were lazy to do it ourselves, but so we didn't have chance to work together. Yes, so this definition of function omega. So we have this property of functions f. You remember in TBA I have some function f which satisfy this relation, and let's compute the variation of the function epsilon, which also enters TBA with respect to radius. So we'll have something like that, and this motivates introduction of convolution between any two functions of two variables. So let me see. It's below, I suppose. Yeah, I don't know. So I have not functions of two variables, but I have a kind of continuous spectrum and discrete spectrum for this theta 1, theta n, I don't know. And so then G and H are, so these are functions, so like we have vector G1, G n, and then G of theta, and then continuous part. Something like that. And then, so the convolution between them is given by this formula. And so now my function omega is given by, if you wish, so I take this special vector of this form, and I iterate my linear equation with this kernel K, which is written here. So this is for continuous part, and this is for discrete parts among themselves, and this is for discrete parts with continuous, and this is for discrete part between themselves. So the integral is like that, and so then so star corresponds to integration with the measure which I introduced before, and then if you wish, I just consider the resolvent of integral operator with this kernel K, and so I sandwich it between these two special vectors, and I obtain this matrix omega mn, and now with this I compute all the 1-point functions. So the difference between this kernel K here and what I had in the TBA equations is that in TBA I had 1 over sine plus hyperbolic plus 1 over sine hyperbolic. Now I introduce inside this parameter. So this is silly like that, but so that is always the case. So now, as I said, so this entire formula is a conjecture. So I cannot prove it from, cannot deduce it from, because you know, in SinhGordon model, as I said, it can be more or less deduced from the inhomogeneous 6 vertex model on a cylinder. So here, I don't know how to, a good, or, okay, there are latest versions of SinhGordon model, but so this is if we are serious about the relation of lattice model and the field theory, so then we have to have some second order phase transition point where and close to this point we obtain our massive model. So I don't know about SinhGordon model whether we can do something like that. So I'm not sure. So nobody explained it to me, but that's why I'm talking about the conjectures. But anyway, so I want to check that all that makes sense. So let us now consider the conformal case, the Liouville model. So, and I have the energy momentum tensor, or so it's one component. So this I consider one chirality for simplicity. So okay, so this repeats for another one. So and it's important to understand that I have from the same thing I define two Virasoro algebras, because you see, if I return to the very beginning, so I have this cycle here, and the integral of the energy momentum tensor over this cycle gives me Virasoro, kind of global Virasoro generators. But also I have local Virasoro generators which correspond to integral over this cycle. This is for counting fields. This is for counting states here and here, right? And correspondingly, So I have these two things here. So this is for local, this is for global. So now I compute these matrix elements in the conformal field theory. So radius here is equal to 1 for simplicity, so it doesn't matter. So it's conformal, so I can do whatever. So and these psi's are created by global generators, as the descendants which I put insert into this point here. Are created by these things. And there is one thing which I have to say that in the conformal field theory also we have this integrals of motion which after the perturbation get promoted to the integrals of motion for the sinh-Gordon model, and they are of all odd spins. So that's and if these two states are the same, then of course the descendants created by local integrals of motion do not count, because you just close the contour and these two guys are the same. Yes, so that's why I am working in the quotient space of Virasoro modular action of this local integrals of motion with all odd spins. And of course, there is no canonical way to choose a basis in the quotient space, but I take some particular one. So I take all the descendants created by even Virasoro generators with even indices, right? So the number is the same, and it's okay. You can show that they are linearly independent. So then phi is the primary field of this dimension, and here as promised, I will give a relation of my fermionic basis to the Virasoro descendants. So first of all, I had this important integer m, which is number of these guys for one chirality. Yes, difference of this number of these guys for one chiralities. And if m is equal to 0, I create pure descendants of this field phi. And so the simplest formula, I like that. So on the level 2, since I am working modular integrals of motion, and the first integral of motion is L minus 1 here. Then modular L minus 1, there is only one descendants, L minus 2, because L minus 1 square I don't care. And so the formula is like that. So there are some very important guys here. Again, gamma functions. Everything is all gamma functions. And so then there are on level 4, this on level 2. On level 4 already I have two guys, beta 1 gamma 3 and beta 3 gamma 1, and they differ here by there is another constant which change sign under my reflection q a to q minus a. So they differ by this sign here and given by this formula. And then I could write you the formula up to level 10, I know, but yes, yeah, but the level 10 is when did I start?
10:30, right?
You started 7 minutes late,
So yeah, I think so.
sorry.
Yes. So let me see. Yes, and so I can write it up to level 10, so if you wish, but so it would be long. So and correspondingly, so now correspondingly, the ultraviolet limit of my function omega can be computed from here, from the formula above. And so you just take, so these guys can be computed with the usual conformal field theory formulae. Right. So then another thing is a little bit more sophisticated when I shift my field. So I have the formula like that, yes. So and I want to know this quantity. So and this is already given by the ratio of two expectation values of primary fields. And of course, the expectation value of primary field in the conformal case is essentially a 3-point function. Yes. So, and knowing the Malotchik of 3-point function, I compute this mass, and so this omega 1 minus 1, which I can compare with my using my equations, is given here. So all this formula. Yeah. So now let me really compare it. So I take numerics. So I will take this radius or dimensionless radius 10 to minus 4 because I want the small thing, and A is for some reason is like that and B is like that. So just I don't know, I compute for this. And for simplicity, I consider only chiral descendants. And I consider the first interesting case, which is level 2 for these guys. Level 2 here, where the spectrum of L0 is degenerate. So I have two things, L minus 2 and minus 1 squared. And then the two eigenvalues of integrals of motion are not distinguished by the first integral of motion, which is L0 here. And you need the third integral of motion. And with the third, you distinguish them. And so there are, this third integral in this basis is 2 by 2 matrix. So you diagonalize it. These are eigenvalues, and these are eigenvectors. And how to identify them with the numbers in TBA, which I had before, I just compute. On the computer, I compute the TBA eigenvalues for this small radius, and I compare them with these two integrals, and I see that one is one and another is another, obviously. So, and then I compute this matrix in the basis L minus 1 squared, L minus 2. I compute my matrix from CFT side. Yes, and so this is some. Yes, this is some. Sorry. This is for the primary fields. Yes, and so for the descendants, it's something more complicated. So for simplest descendants, L minus 2 is something like that, but then it fastly gets complicated. So, and this is my CFT answer, and it must be compared with what I computed from my equation starting from TBA for omega 1, 1, this is for omega 1, 3, 3, 1, and then for omega 1 minus 1, it is from the ratio of two primary fields. And the results. So you see, so the results are pretty good. So here is very good. So this is for the one eigenvalue, this is for another. So this is for for level 1, this is for level 3, and this is for ratio of shifted primary fields. So kind of I am doing quite well. And so this is an important check of my conjecture. So probably some of young guys will produce a proof one day. So this conjecture, I'm not sure, but I'm sure that it will. But so so this supports my conjectures, and another support is that so I was talking about the kind of high temperature limit when radius is small, and so there is another limit when radius is sufficiently large. So then you can apply some analog, or for ground state you can apply what's called Leclerc-Musarda formula. But so for diagonal matrix element, there is some formula which was found by Posh guy. So I am a little bit with Hungarian names, it's not obvious for me. So, but anyway, so we compared with this, of course, and everything fits. So that's why we are sure that we found correct formula for the diagonal matrix elements. And so it would be, for example, interesting to apply them to compute the one-point function of the torus, which is not a trivial problem even in the conformal field theory case. Thank you very much.
Okay, thanks a lot for your talk. Are there questions?
Thank you. So there are two modes. One goes to the left and another goes to the right.
Right. Yes.
If they, in conformal limit, they probably stop talking to each other, right? One goes to the left, one goes to the right. Most conformal, they stop talking to each other.
Yeah, sure.
And the correlation functions kind of a direct product of holomorphic and anti-holomorphic.
Yes, for sure.
But before conformal,
no, for descendants, not for primary, suppose.
yes. But before the limit is taken, they slightly interact.
Sure. Yes.
Can you compute the next correction which shows how do they interact?
Another interesting question is nobody could explain to me that you see. So I have exact formula, even if I consider the ground state. Yes, I have an exact formula for one-point function for SinhGordon, rather explicit for the ground state. Yes. So now, if I consider just three part of this. Just exponent, yes, logarithm of kind of in classical limit. So then I will get the classical action on what? On so I have a cylinder and I have one insertion and I consider fields which behave around this insertion as in real world, the same thing, right? So this thing. Of course, it was computed long ago, and so of course everything coincides, so that's fine. But now, if I consider the first quasi-classical approximation, I am supposed to have determinant of in the background, right, of this field, and I have an explicit description for this determinant. Can anybody compute this determinant for you take classical SinhGordon equation and you consider the solution which on a cylinder which prescribes singularity at one point, and can you compute a determinant? I mean, so the Laplace determinant in this background. So nobody knows. So at least nobody can answer me.
Other question? Okay, so maybe I have one. So the correction to TBA are what are the type of correction you get? I didn't understand because you have deviations, no, from TBA. Are this 1 over? It is 1 over R.
Where is it?
So I thought that TBA as finite R corrections, no?
TBA. Let me restart. Let me see. So this is TBA, and so I consider you mean this additional particles here. I mean the entire spectrum. But this is I think this is well known that if you want to so the vacuum corresponds to the case when the these thetas are absent, and otherwise, so this is exactly why I consider SinhGordon, because it's very simple. All these guys are real, and so these are very well defined. The entire spectrum is computed easily.
Okay. Okay, no more questions. Okay, let's thank the speaker again.
Okay.